Hello. This is a little mini lecture on chapter 3. We're going to go through chapter 3 pretty quickly, and we'll do kind of a little experiment in class that'll help you understand this a little better too. But this is about propagation of error and uncertainty, a quick version. All right. So 3.1 you didn't have to take notes on because they do a lot of things that are kind of redundant. But really, this is what's going on. When we take a measurement, the accuracy and the precision and everything of that measurement is limited by our measuring devices and our ability to read them. So there's error involved, right? So just think about it. You're like, your 21-year-old eyes, we're probably are better at reading a thermometer than my 56-year-old eyes, right? So you probably have less error if you're reading your thermometer, right? But there's always error when you do a reading, okay? Partially it's because things are continuous. When we use those readings, so once we get these readings that have errors in them, and we use them in formulas for other things, that error can grow. It's called propagation of error, and the calculations can become kind of distorted because of that error, and we need to know how much error is there. So our goals in any measurement are accuracy and precision, and getting the most accuracy and precision that we can have. So here's what's going on. We have a series of readings. You could think about like taking a temperature of something over and over and over and over, and notice those readings might be different. And for each of those measured values, there's really a true value, right? Like the real temperature that it is at that moment. And then there's some bias, and that's sort of a systematic kind of error. Like maybe the thermometer that I have always reads low, okay, or something like that. And then there might just be some random error, all right, just things that are just kind of random reasons that maybe sometimes maybe my eyes read it too high, sometimes read it too slow sometimes, and we assume that kind of averages out over time, okay? So that's what's going on when you take measurements. There's a real value, but there's going to be bias and error, just random error involved too. All right, so here's kind of like a table of just sort of the terminology that you're going to see within this chapter. What we're going to do is we assume that all measurements, M's, okay, they have a mean and they have a standard deviation, okay, which are unknown values, right? So when you take a measurement, there's a real mean, there's a real standard deviation. They vary, right? Your measurements vary. We're going to take a large sample of readings, M1 through Mn, and calculate X bar. Sorry, couldn't write that. A sample mean and a sample standard deviation. Okay, and we're hoping that X bar and that sample standard deviation sort of are close to the mean mu and the standard deviation sigma. Okay. So the things we're interested in is increasing, improving our bias and improving our uncertainty. And this bias is the real mean minus the true value. Okay, so we have these M's that are all different measurements. They have a mean. And then there's like a real value too for that thing, right? Whatever the difference is called the bias. X bar, we're going to estimate this bias by X bar, or sample mean, minus an estimate of the true value, and we call that calibration. Our uncertainty in any of these measurements is the standard deviation. We're going to estimate that by a sample standard deviation. Most of the measurements are going to be given in the form of the measurement plus the uncertainty. This uncertainty is going to be either an S or a sigma, just so you know. Okay, so if you under this in your notes, under uncertainty, you might write S or sigma. Okay, so that's kind of what we're going to be dealing with. Some measurement plus or minus uncertainty. Okay, so anyway, really our goals are to get better accuracy. So you'll see I've added another column here. When we have good accuracy, it means our bias has decreased. That means our mean and our true value are very close to each other. In other words, we have really good calibration of whatever we're using to measure things, okay? So accuracy means we have low bias. Precision means we have low uncertainty. We've talked a lot about precision in class, right? We've talked about how we like to have low standard deviations. Okay, so that means low uncertainty. So precision increases when uncertainty decreases. So that's kind of our goals here. You're going to see some big uncertainty in a second. All right, in 3.2, some of this is going to look pretty familiar to you based on other things we did when we talked about linear combinations of measurements. So our goal is to estimate a measurement and its uncertainty for linear combinations or averages of groups of measurements. So what I want you to do right now, because I did not want to have to write these formulas down because it just takes forever, stop the video now and write the formulas from 3.2. You don't have to write them all. It's like page 170 to 172. There's a few formulas, but I want you to have them in front of you as you proceed here. All right. So stop and do that, and then come back. All right, you're back. All right, so notice in this book, they're always going to state measurements in the form of this measurement plus uncertainty, and that uncertainty will be either a standard deviation of like a population standard deviation or an S. Okay, so here's an example. Suppose the measurement of the radius of a disk, all right, a circle, is given by 2 plus or minus 0.2 centimeters. So this is our measurement, 2, and 0.2 centimeters is some sort of uncertainty measure, maybe a standard deviation. We want to estimate the circumference and the uncertainty of the disk's circumference, okay? So an estimate of that, this should be the first formula you wrote down. The estimate of the circumference should be 2 times pi times r. And if we take 2 times pi times this radius was 2, right, our estimate of the radius was 2 centimeters, we'll get 12.6 centimeters. And then the uncertainty will be 2 times pi, right, that's the constant, the multiple, right, times r. Well, we're going to take 2 times pi times the standard deviation. That's the formula you have, right? Absolute value of c times the standard deviation, and we get 1.2 centimeters for the uncertainty. And what we say is that the circumference is 12.6 plus or minus 1.26 centimeters. So notice our old uncertainty was 0.2 centimeters for the, just for the radius, but now it's grown, right? Now the uncertainty is 1.26 centimeters for the circumference. It's bigger for the circumference because of that formula, that function. All right, let's look at what happens when you go on to a nonlinear function of a measurement. All right, so now we want to look at like how to estimate a measurement and its uncertainty for a nonlinear function of a measurement, right? Like an area or something like that. Stop the video now and write down the formulas in 3.3. Specifically, write down 3.10 and then the page 182 summaries. Okay, that's all we're using. All right. This requires a understanding of derivatives. So hopefully you remember how to do derivatives. Here's the example. We're going to use the same thing. Suppose the measurement of a radius of a disk is given by 2 plus or minus 0.2 centimeters. Estimate the area and its uncertainty. So area, right, that's a quadratic function of radius, right? It's r squared, not just r. An estimate of the area is pi times r squared. So notice we're going to do pi times 2 squared there. And I'll fill that in a second. And the uncertainty is going to be the derivative of this function, right? So in your formula from 3.10, you have u here. That's the function, pi r squared, with respect to r times 0.2 centimeters, right? This standard deviation for r. Okay, I'm going to leave it. I'll fill these in and come. Okay, so an estimate of A is pi times r squared. The radius, right, was 2. This is the 0.2 is the uncertainty in the radius. So pi times 4 is 12.6 centimeters squared. But the uncertainty in this estimate is going to be the derivative of pi r squared dr times sigma, right? The derivative of this, right, you have to use the power rule, 2 pi times r times sigma. So 2 pi r sigma is 2 times 2 pi times, oh, I have an extra 2 in there. Get rid of one of these 2's. All right, so 2 pi times 2 times 0.2, and that's 2.51 square centimeters. All right, get rid of one of the 2's. The area should be 12.6 plus or minus 2.51 centimeters squared. So notice when we start looking at area, right now the error has doubled again. The uncertainty in that estimate, right, started as 0.2, then it went to 1.2 something, 6. Now with area, right, when we go non-linear functions, the error has increased. The amount of uncertainty in our estimate is like a scale, kind of a scaled up version. It's really propagating itself. So that's what happens with error. That's why it's important to kind of keep track of error and understand how it grows. Okay, we'll do an experiment in class and we'll practice this a little bit when I see you. All right, thanks. Bye.